Welcome back to Tech Talk. Today, we're diving into a fascinating paper that's shaking up the world of real time object detection. Joining me is Jan, lead researcher on this groundbreaking project, and G, a leading expert in computer vision. Jan, why don't you start by telling us about the core problem you were trying to solve?
Thanks, Sarah. So, real-time object detection is crucial in fields like self-driving cars, surveillance systems, and even robotics. But existing methods, primarily based on convolutional neural networks like YOLO, often struggle to achieve both speed and high accuracy. One major culprit is their reliance on a post-processing step called non-maximum suppression, NMS, which takes time and introduces instability.
That makes sense. So, what about these transformer based methods? They've been gaining traction in other areas of computer vision. Are they the answer?
They certainly offer promise. DETR, short for detection transformer, is a groundbreaking model that eliminates the need for NMS. It's elegant and efficient, but it suffers from a major drawback. It's computationally expensive, making real-time performance difficult.
So, that brings us to RT-DETR. Jan, can you explain what it is and how it's different?
Absolutely. RT-DETR, short for real-time detection transformer, is the first, to our knowledge, end-to-end real-time object detector based on transformers. It tackles the limitations of both YOLOs and DETRs by combining the best of both worlds. Think of it as a hybrid approach. It involves two key innovations: an efficient hybrid encoder and an uncertainty minimal query selection scheme.
Let's break down these innovations, Jan. Start with the efficient hybrid encoder. What's so special about it?
Imagine you're building a puzzle with pieces of different sizes. You wouldn't just dump them all together and try to fit them all at once, right? That's what traditional multi-scale encoders do, and it's inefficient. Our hybrid encoder decouples the process. It treats features from different scales separately, first focusing on intra-scale interactions within each scale, and then combining them in a more efficient cross-scale fusion step. It's like tackling the puzzle one section at a time, making the whole process much faster.
That's a great analogy. It really clarifies the concept. GA, from your perspective, how significant is this decoupling approach? It's a clever solution. Traditionally, multi-scale features in transformers have been a computational bottleneck, leading to slower inference times. By decoupling the interaction process, RT-DETR significantly reduces the computational load without sacrificing accuracy. It's a step in the right direction for making transformer-based object detection practical for real-time applications. Okay, so we've covered the encoder. Let's talk about query selection. Jan, explain why this is so important in DTR models and what makes RT-DETR's approach different.
In DTR models, queries act like pointers, guiding the decoder towards objects in the image. Think of them like search terms. If you use the wrong search terms, you won't find what you're looking for. Traditional query selection schemes rely solely on classification scores, which only tell you how confident the model is about the object's category. RT-DETR takes it a step further. It optimizes for both classification and localization confidence, ensuring that the selected queries are accurate and precise. This is like using more specific and targeted search terms, getting you much closer to the right answer.
So, instead of just looking at how confident the model is about the category, RT-DETR also considers how well it can pinpoint the object's location. That's a crucial distinction.
Exactly. This uncertainty minimal approach results in a significant improvement in accuracy. We validated this through a comprehensive ablation study where we analyzed the impact of each design choice on performance.
Let's get to the results, Jan. What did you find?
We compared RT-DETR with state-of-the-art YOLO and DETR models and found that it consistently outperformed them in both speed and accuracy. RT-DETR achieved an impressive 53.1% AP on Coco Val 217 while maintaining a speed of 108 FPS on a T4 GPU. That's significantly faster and more accurate than even the most advanced YOLO models.
Wow, those are incredible results. GA, how do you think this impacts the field of real-time object detection? This is a game changer. RT-DETR has shown that transformer-based methods can not only achieve high accuracy, but also reach real-time performance, finally addressing the limitations of traditional CNN-based methods. It opens up exciting possibilities for applications requiring both speed and precision. Ian, are there any limitations or areas for improvement in RT-DETR?
While RT-DETR outperforms the current state of the art, it still struggles with detecting small objects. This is a common challenge in object detection, and we're actively exploring ways to improve performance in this area. One promising direction is knowledge distillation, where we can transfer knowledge from larger, more accurate DETR models to RT-DETR, effectively boosting its performance.
That's an interesting approach. GA, how do you see these limitations impacting the practical applications of RT-DETR? While the small object detection limitation is a concern, it's important to remember that RT-DETR's success in other areas opens up possibilities for a wide range of real-time applications. It's a valuable step forward, and ongoing research in areas like knowledge distillation can further address these challenges. This research also highlights the need for continued development of transformer-based methods for object detection. Jan, to wrap up, what are the key takeaways from this research, and what are the future implications?
The main takeaway is that RT-DETR has successfully bridged the gap between speed and accuracy in real-time object detection. It's a significant step forward, offering a viable alternative to traditional CNN-based methods. Looking ahead, we're excited to explore how RT-DETR can be applied in various applications, pushing the boundaries of real-time object detection even further.
GA, any final thoughts on the paper's significance and potential future directions? This research is a testament to the power of transformer-based methods in object detection. RT-DETR's success opens doors for further innovation in real-time applications, demanding new research directions. We can expect to see continued development in areas like small object detection, knowledge distillation, and the application of transformers to other challenging tasks in computer vision. That's a great perspective, GA. It seems like we're entering a new era of real-time object detection, thanks to the exciting breakthroughs like RT-DETR. Jan, thank you for sharing your research with us. And GA, thank you for your insightful commentary. This has been a truly fascinating discussion. And to our listeners, remember to stay tuned for more insightful conversations about the latest advancements in technology.